Did you know that even as you lie still, our solar system is rising and falling through a galaxy that never rests? Right now, you drift inside a scene shaped by ancient violence. Our solar system rests in a vast cavity carved by exploding stars, wrapped in a veil of unseen matter that outweighs everything visible. Above and below, great structures rise and fall across thousands of light years. A ring of old supernovae once swept this region clean. Dark matter encloses the galaxy in a silent halo that we can sense but never touch. The gravity of the Milky Way rattles distant comets far beyond the sun's warm reach. If you feel drawn to the mysteries hiding around us, then let me guide you into this vertical realm. Picture the Milky Way as a wide spinning disk of light, thin and bright. Most stars cluster near the center, pressed into the midline where gravity holds the galactic disk together. You might expect our sun to lie there as well, resting among the crowded stars. It does not. Our entire system floats 55 light years above that central layer, which is 324 trillion miles north of the galaxy's densest region. Scientists confirm this by using gamma-ray telescopes that see through dust and gas, fixing our three-dimensional position with remarkable precision. The result is clear. We are not sitting where simple models would place us. The galactic plane stretches 100,000 light years across, yet only 1,000 light years thick, shaped almost like a dinner plate. The sun should rest somewhere on that plate, yet instead it hovers above it, suspended in the empty space between the dish and the table. That offset changes the nature of what surrounds us. Many imagine space as a uniform sphere around Earth. They assume wonders and dangers spread equally in every direction. That picture is wrong. When you gaze toward the northern galactic pole, you look into a vastly different environment than when you look toward the south. The shapes differ, the densities differ. Even the temperature of invisible gas shifts between those two directions, though scientists continue to debate the cause. Because we sit above the galactic disk, we receive less radiation from the central region. The supermassive black hole, 4 million times heavier than the Sun, lies 27,000 light years away and sits below us in that crowded plane. Its outbursts pass through layers of stars and gas before they reach our elevated perch. Some researchers propose that this position shielded early Earth, giving life a chance to take hold without being overwhelmed by cosmic rays. Yet there is a reason astronomers remain uneasy. Our height is temporary. The sun does not stay 55 light years north. It rises and falls. It drifts up and down through the galactic plane, like a weight on a spring, crossing that dense disk again and again. Right now we are moving farther north at about 4.5 meters per second. The last crossing happened 3 million years ago, at the time when early humans first walked upright in Africa. The next crossing will come in 30 million years, provided nothing massive disrupts our course. Each passage carries us through regions packed with gas and gravitational turbulence that may disturb the icy comets circling the solar system's edge. This steady vertical motion continues because unseen forces tug on us from both directions. Forces that never rest, forces that treat the sun as if it were a toy, suspended on a string, pulling it through layer after layer of the galaxy. To picture this, imagine dropping a ball through a tunnel, drilled straight through Earth. The ball accelerates toward the center, rushes past it, climbs toward the far side, then falls back again. It oscillates endlessly like a pendulum moving through vertical space. Our sun performs the same motion as it travels through the Milky Way. Every 26 million years, the solar system completes a rising and falling journey through the galactic plane. Astronomers confirm this gentle rhythm by tracing the positions of the stars and calculating the gravitational pull that threads through our galaxy. The numbers leave no doubt. We move like a celestial pendulum. Here is how this motion unfolds. The galactic disk holds most of the visible mass of the Milky Way. Stars, clouds of gas and drifting dust all lie within that thin and sprawling structure. When the sun sits above the plane as it does now, the weight of that mass beneath us creates a steady pull downward. Every star and every drifting particle draws us back toward the central layer, so we begin to fall slow at first, then faster. At the moment we drift north of the plane, yet our climb is fading. Soon we will stop rising, pause for a breath of cosmic stillness, then slip downward toward the midline of the galaxy. As we cross the plane, our speed will rise to about 6 meters per second or more. That motion will carry us past the center and out toward the opposite side. Then the process reverses. Once we fall below the galactic plane, the mass above us pulls upward again. We slow, we stop, and then we turn. We rise northward once more. The cycle continues endlessly. It is repeated hundreds of times across the 4.5 billion year life of the Sun. Yet the motion is not as simple as a pendulum gently swinging in the night. Another force acts upon us. Dark matter, this unseen substance, forms most of the galaxy's mass. It surrounds the Milky Way in a vast halo that reaches far above and below the shining stars. Dark matter adds roughly 15% more gravitational pull to our vertical motion. Scientists work this out by measuring our speed and calculating what extra force must be present. In the 1980s, some researchers offered a troubling idea. They proposed that each passage through the galactic plane carried us into regions of denser matter, regions that might disturb the Oort cloud and send waves of comets toward Earth. They named it the extinction theory. For a moment, extinction events on Earth seemed to align with the 26 million year crossings. The idea looked persuasive. Then improved dating of those events revealed that the pattern was not as precise as once believed. The theory collapsed under closer study, yet something still unsettles astronomers. Our journey does take us through changing cosmic environments. The density of gas, the strength of magnetic fields, and the intensity of radiation all shift as we rise and fall through the galaxy. These changes influence the distant edges of the solar system. Our slow oscillation means Earth has lived through many different galactic neighborhoods. Life has unfolded as the Sun traveled through calm eras and violent ones. What awaits us during the next passage through the plane we cannot know, but physics assures us the answer will arrive in about 30 million years. Unless something else reaches us first, something already drifting toward us from the great emptiness. You live inside a bubble 1,000 light-year wide. Its walls are made of compressed gas. Its interior is almost perfectly empty, one of the most extreme vacuums ever observed. This is not a natural structure. It is the remnant of ancient violence. Scientists call it the local bubble. They confirmed it with X-ray observations that revealed the hot gas shaping its boundaries, and with optical surveys that traced how nearby stars cluster along its shell. Every star within 500 light years of Earth lies on that shell. None sit in the hollow space. We drift inside a cosmic chamber carved long ago. The interior holds only about 1,000th of an atom per cubic centimeter. That is 10 million times less dense than the air you breathe. Even our finest laboratory vacuums are still 10,000 times denser than a typical interstellar cloud, and that cloud is itself thousands of times denser than the local bubble. The emptiness here is astonishing. Yet something else is even more remarkable. The gas inside is extremely hot. Not warm, but close to 1 million degrees Kelvin. By contrast, the local interstellar cloud that surrounds our solar system is merely warm at 7,000 degrees, with a density of 0.3 of an atom per cubic centimeter. Two entirely different environments press against each other. How does gas reach 1 million degrees in such isolation? Only one source can create heat on that scale: supernova explosions. Great stellar storms that rip themselves apart. Not a single detonation, but many. Massive stars dying in sequence. Each blast pours energy into an expanding void, heating the interior to temperatures so extreme that any solid material would vanish in an instant. Astronomers followed the clues back through time. They measured the motion of nearby clusters and traced when the giant stars in our region must have met their end. The timeline leads to roughly 10 to 20 million years in the past. Not one event, but a chain of perhaps 15 or 20 separate detonations. Each one injected energy into the growing cavity, driving its walls outward, sweeping up gas and dust, and carving out the vast emptiness we now drift within. And consider this, our solar system was already here. Earth had formed. Life flourished in ancient oceans. Meanwhile, somewhere in our galactic neighborhood, enormous stars were running out of fuel and exploding one after another in a cosmic relay. Each blast sent shock fronts racing outward at thousands of miles each second. Each one heated the surrounding gas to millions of degrees. With every detonation, the bubble expanded. We escaped only because the shock waves weakened as they traveled. By the time those waves reached our position near the edge of the forming cavity, the violence had faded enough to spare Earth's atmosphere. Yet the evidence hints at something far more unsettling. We might have been inside the bubble as it grew, wrapped in the expanding hollow, bathed in radiation and high-energy particles for millions of years. Scientists have found that we are now drifting toward the outer boundary of this local bubble. In several million years, we may emerge from it if another dense cloud does not cross our path first. But the bubble itself has not stopped. It continues to expand, though at a slower pace than during those ancient blasts. Its walls push outward into interstellar space, compressing gas at the edges and possibly sparking the birth of new stars. And there is a sobering thought. Every star has a lifespan. Every massive star ends in a violent death. The local bubble is bordered by young luminous stars, arranged in a structure known as Gould's Belt. Some of those stars will explode in the future. The scene is still active. The killers may not be finished. 15 giant stars perished to create the space we call home. Each one burned with an intensity our sun can never match. Each lived fast and used its fuel in only a few million years. Then each one exploded with more energy than our sun will release over its 10 billion year lifetime. These were not remote events. They occurred in our own cosmic neighborhood. The most likely source of the local bubble is a group of stars known as the Scorpius-Centaurus Association. This cluster of massive hot stars lies about 400 light years away, positioned right at the bubble's rim. Computer simulations show that a sequence of supernova in that region could sculpt a cavity identical to the local bubble we observe today. Here is how a supernova creates such a structure. A massive star, perhaps 20 or 30 times heavier than our sun, begins by fusing hydrogen into helium in its core. Then helium becomes carbon, carbon becomes oxygen. The fusion marches up the periodic table, building heavier elements. But when the core begins to fuse iron, the process no longer generates energy. It drains energy. The core collapses in less than 1 second. Matter plunges inward at nearly a quarter of the speed of light. The collapse is so sudden that the outer layers cannot respond. They pause in space for a brief moment, while the core implodes beneath them. Then the core rebounds. The rebound drives a shock wave outward through the star at thousands of miles each second. The star rips itself apart. The explosion releases more energy in a few seconds than 100 billion ordinary stars emit in that same moment. That energy sweeps outward, heating nearby gas to millions of degrees and accelerating it to supersonic speed. The expanding remnant grows like a cosmic crater, larger each year. Now imagine 15 or 20 such explosions in the same region of space over 10 million years. Each blast pours fresh energy into the growing cavity. Each one pushes the walls of the bubble a little farther into the void. Together they sculpt a structure far larger than anything a single supernova could create. We call this vast creation a superbubble. Yet the violence does not end with the explosions themselves. Shock waves from many supernova race outward and collide with each other and with the surrounding interstellar gas. Where these shock fronts converge, they squeeze the gas into dense sheets. Sometimes these compressed regions collapse under their own weight. New stars ignite. The cycle continues. Massive stars are born. They burn through their lives with astonishing speed. They explode. They carve out new bubbles, and they spark the birth of more stars. Scientists uncovered physical evidence that these distant explosions touched Earth. The clues rest inside deep ocean sediments. When researchers drilled into the seafloor and examined the layers, they found elevated levels of iron, 60A radioactive isotope that does not form naturally on Earth or within our solar system. Its only known source is a supernova. The iron 60 peaked twice. One peak formed roughly 1.7 to 3.2 million years ago. The second appeared around 6.5 to 8.7 million years ago. These peaks match the times when our solar system would have passed through debris clouds from the supernova that shaped the local bubble. Radioactive atoms drifted down from space, settled in the ocean, and remain there as silent markers of the past. The proof lies buried in the mud. And this is what unsettles astronomers. We do not know the exact position of the solar system when those explosions occurred. Perhaps we were near the edge of the emerging bubble, shielded by distance. Or we might have been far closer, exposed to radiation levels far beyond what Earth's magnetic field and atmosphere could easily deflect. The radiation may have influenced mutation rates in life on Earth. It might have nudged evolution forward during those epochs we endured, yet something inside us may have shifted in ways we still do not understand. Deep beneath the Pacific Ocean, hidden in sediments that have gathered for millions of years, lies proof that our solar system moved through the remnants of a supernova. The evidence is real. You could hold it in your hand if you drilled deep enough. It carries the faint glow of radioactive decay. The isotope is iron 60. This form of iron holds 26 protons and 34 neutrons in its nucleus. It is unstable. It decays with a half-life of 2.6 million years, releasing radiation as it transforms into more stable elements. It cannot form naturally on Earth. It cannot arise from normal processes in our own star. Significant amounts appear only in the core of a supernova. Scientists found the iron 60 by chance in the 1990s while studying deep-sea ferromanganese crusts. These crusts grow with extraordinary slowness on the ocean floor, adding layers of metal compounds at just a few millimeters every million years. By slicing the crusts into thin sections and dating each one using other radioactive isotopes such as beryllium, 10 researchers built a timeline that revealed how material falling from space changed over millions of years. Some layers held normal amounts of iron, others contained iron 60 far above the background level. The spikes rose sharply, showing that the isotope arrived during specific intervals rather than as a steady drizzle. When the layers were dated, 2 peaks emerged. One formed about 2 million years ago, give or take a few 100,000 years. The other appeared around 7 million years ago with similar uncertainty. The timing matched predictions for when the supernova that created the local bubble would have released their debris and when Earth would have crossed those clouds. The alignment was too precise to dismiss. Scientists had uncovered physical proof that Earth passed through the aftermath of nearby stellar explosions. But iron 60 was not alone. Researchers later discovered manganese 53 in the same layers, another isotope born in supernova. They also identified plutonium 244, which likewise cannot form naturally on Earth. Together, these isotopes strengthened the case. They were not errors. They were not contamination. They were genuine visitors from ancient cosmic events. The discoveries answered some questions and opened new ones. How much radiation washed over Earth during those passages through supernova debris? The iron 60 itself posed little danger because it arrived in tiny quantities. A few atoms scattered across an entire world. The presence of iron 60 tells us that an entire wave of stellar debris once swept across our world, and that wave must have carried far more than dust. It would have brought high-energy cosmic rays, gamma radiation, and X-rays. All of it would have pressed against the atmosphere of Earth. Some researchers propose that this radiation may have influenced life, raised mutation rates, disturbed ecosystems, and perhaps even nudged certain species toward extinction if the dose reached extreme levels. Yet the story remains uncertain. Life endured. No major extinction event aligns perfectly with the peaks of iron 60. Either the radiation never reached truly destructive levels, or the magnetic field and atmosphere of Earth shielded the surface with remarkable resilience. In recent years, scientists found the same isotope in Antarctic snow, in lunar samples, and in cosmic dust gathered by aircraft flying at high altitude. It is still arriving today, though, in amounts far smaller than during the ancient peaks. This means we continue to drift through the lingering edges of those long-forgotten explosions. Even after millions of years, their debris still brushes against us. These radioactive traces reveal something profound. Earth does not journey in isolation. We move through the galaxy, and the galaxy leaves signatures upon us. The supernovae that shaped the space around us did not erupt at a safe distance. Their influence reached Earth. Their marks remain in the ground beneath our feet, in the oceans, and perhaps even within our genetic story if past radiation played a role in evolution. In a real and intimate way, we are built from the remnants of dead stars, and we still carry the evidence of the forces that forged our cosmic neighborhood. At this moment, Earth is gliding through a cloud, though not a cloud of weather. It is an interstellar cloud composed of hydrogen, helium, and small traces of heavier elements. It surrounds the entire solar system like a soft envelope of warm gas stretching across several light years. Scientists refer to it as the local interstellar cloud, and it is not still. The cloud spans roughly 30 light years, though its edges taper gradually, rather than forming a sharp boundary. Its temperature is close to 7,000 Kelvin, which sounds fierce, yet counts as warm on the scale of interstellar space. Its density is about 3/10 of an atom in each cubic centimetre. The air you breathe contains around 30 billion atoms in that same space. The cloud is nearly empty, yet still 300 times denser than the bubble of space that holds it. Now the story becomes even more intriguing. The cloud moves, relative to the solar system, at approximately 16 meters per second. The solar system itself moves through the galaxy at about 140 meters per second. Together, these motions create the local interstellar wind. A slow stream of gas drifts through our solar system at nearly 16 meters per second from the direction of the constellation of Fucus. It does not behave like a terrestrial wind. Space is far too thin for that. Instead, atoms and ions slide past the solar system, much like raindrops passing a moving car. Some particles slip into the heliosphere, the bubble carved out by the solar wind. Most bend around it, steered by magnetic fields and the pressure from our sunday. Astronomers confirm the existence of this cloud by studying the absorption of starlight. When light from distant stars travels through gas-specific wavelengths vanish, depending on the elements present. By examining these absorption features across many stars, researchers trace the cloud's position, temperature, density, and chemistry. The cloud is real. We are inside it. It is partially ionized, with some atoms stripped of electrons by ultraviolet light from nearby stars. These charged particles respond to magnetic fields and create intricate patterns that neutral gas cannot form. What unsettles astronomers, if only slightly, is a simple question. How long have we been inside this drifting cloud? The best estimates suggest that our solar system drifted into the local interstellar cloud, somewhere between 44,000 and 150,000 years ago. In the language of the cosmos, that moment happened almost yesterday. Before that passage, we moved through another part of the local bubble, a region shaped by different temperatures, different densities, and different gas conditions. The cloud flows through the bubble, and we travel through it as well. Yet our paths and speeds do not match. Eventually, perhaps in 10,000 to 50,000 years, depending on which model you prefer, we will slip out of the local interstellar cloud and cross into a new environment. It might be another wandering cloud. It might be a more empty patch of space inside the bubble. When that crossing happens, the conditions around us will shift. The gas density that surrounds the solar system will change. The flow of interstellar material entering the heliosphere will rise or fall. Some scientists suggest that these slow changes might influence Earth's climate across immense timescales. A denser flow of gas could press slightly on the heliosphere. That gentle pressure might allow more cosmic rays to reach Earth's atmosphere. Those rays would ionize particles high above the surface, That ionization might guide the birth of clouds and alter long-term climate patterns. The effects would be delicate, too soft to trigger an ice age or a global catastrophe, yet it might leave a signature in climate records that stretch across tens of thousands of years. The local interstellar cloud is only one piece of a larger network, a family of drifting clouds that wind through the bubble like currents in a deep ocean. They carry names such as the G cloud or the Ursa Major moving group. They meet, separate, and bend around obstacles shaped by stellar winds and magnetic fields. Our solar system swims through this shifting sea. The currents ahead remain unknown. New clouds, new densities, new mysteries waiting in the dark. And surrounding our solar system like a tilted crown is a ring-shaped structure filled with young and powerful stars, destined to explode within the next few million years. This ring spans 3,000 light-years and tilts 20 degrees above the galactic plane. Astronomers call it Gould's Belt. It wraps around us completely. In the 1800s, Benjamin Gould noticed that many of the brightest stars in the sky gather along a great circle, tilted away from the Milky Way's glowing band. That arc marks the belt, a ring of recent star birth containing thousands of hot young stars racing toward violent ends. Within that ring lie some of the most iconic star-forming regions visible from Earth. The Orion Nebula lives there. So does the Scorpius-Centaurus Association, the same cluster of stars whose ancient supernova explosions carved out the local bubble. The belt is rich with stellar nurseries, places where dense clouds collapse under gravity and ignite into new suns. What sets this structure apart is its orientation. Most star formation in the Milky Way unfolds inside the galactic plane, where dust and gas gather, yet Gould's belt rises above and falls below that plane, forming a tilted ring suspended in space. Its origin remains debated. A leading idea proposes that a powerful supernova or a collision with a gas cloud roughly 30 million years ago sent a wave of star formation sweeping outwards, sculpting the pattern we now see. The stars in the belt are young. Most formed less than 30 million years ago. Some continue to form even now, hidden inside warm shells of dust. Many of these stars belong to the O-type and B-type families. They shine blue-white with astonishing heat and mass. They burn through their fuel in only a few million years, then explode as supernovae. The danger of the belt lies not in its shape, but in its constant change. Star formation persists. New massive stars ignite, each one a future explosion waiting to happen. Their supernovae will pour fresh energy into the surrounding space. They may continue to stretch the local bubble. They may spark new rounds of star birth. Some of those stars have already died. Their light has simply not reached us yet. A star 500 light years away might have exploded 400 years ago. The light from that event is still moving toward us. When it arrives, a brilliant new point will blossom in the night sky. It may shine even during the day. It may linger for weeks or months before fading back into darkness. The nearest massive star in this region of the sky rests around 400 light years away. That is remarkably close on a galactic scale, close enough that a supernova there would blaze across our sky. Yet it is distant enough that its radiation would not strike Earth with lethal force. Real danger comes from stars only a few dozen light years from us. At such distances, gamma rays and X-rays from an exploding star could wash through Earth's atmosphere. They could erode the ozone layer and raise the level of radiation reaching the ground. This is why astronomers watch the massive stars near us with constant care. They search for hints of instability that might signal an approaching collapse. A dying star swells as it burns through its final fuel. It sheds material in fierce stellar winds. Its light wavers and dims in patterns that hint at turmoil within. At the moment, none of the stars in this belt show clear signs that an explosion is imminent within the next few centuries. Yet predictions remain uncertain. Stars can behave in unexpected ways. The belt also holds many smaller clusters of stars. These are families of stars born from the same clouds of gas at roughly the same moment. They drift together through space, slowly spreading apart over millions of years as each star follows its own path around the galaxy. Earth belongs to no such group. Our Sun formed 4.5 billion years ago in a different region entirely. It wandered through the galaxy until it arrived here. Now we find ourselves inside this vast belt, surrounded by stars that will end their lives long before our Sun grows dim. We inhabit a ring of cosmic fire, and that fire still burns. Our world sits inside a great bubble, sculpted by the Sun. This bubble shields Earth from the wider galaxy. Without it, interstellar radiation would strike our atmosphere with full and relentless force. Cosmic rays would rain down unceasingly. Life as we know it might never have emerged. This shield is the heliosphere, and it has boundaries. The Sun throws charged particles into space every moment. Protons, electrons, helium, nuclei, all racing outward at speeds between 200 and 500 meters per second. This flow of particles is the solar wind. It expands outward in every direction and fills the space around the Sun with a hot and magnetized plasma. The solar wind does not end at the planets. It continues to expand until it meets resistance. That resistance comes from the interstellar medium. Gas and dust between the stars press inward from all sides. Where the outward push of the solar wind matches the inward push of the interstellar medium, a boundary appears. This boundary, known as the heliopause, marks the outer edge of the heliosphere and the start of true interstellar space. For many years, scientists estimated its location using models that describe the fading of solar wind pressure with distance and the counterpressure of the interstellar medium. These models place the heliopause somewhere between 80 and 150 astronomical units from the Sun, though uncertainty remained because we did not know the exact density of the surrounding gas. Then Voyager 1 reached it. On the 25th of August in the year 2012, at a distance of 121 astronomical units, Voyager 1 recorded a sudden fall in solar wind particles, a rise in galactic cosmic rays, and a shift in the magnetic field. It had crossed the boundary into interstellar space. The data confirmed that the transition occurred almost exactly where theory placed it. Yet one surprise emerged. The heliosphere is not a perfect sphere. Early models imagined a round bubble expanding evenly. Reality is far more complex. Measurements from several spacecraft, including the Interstellar Boundary Explorer mission, revealed an uneven shape. It may resemble a teardrop or something even more irregular. The form depends on the direction of our motion through the interstellar medium and on changes in its density and magnetic forces. The local interstellar cloud that surrounds us presses unevenly against the heliosphere. In the direction of our travel, the upstream side, the heliosphere, is compressed as our motion creates a ram pressure effect. On the downstream side, the boundary stretches farther into space where pressure is weaker. Some theories propose a long trailing tail shaped by our journey around the galaxy, though this remains uncertain. Inside the heliosphere, the solar wind protects us from most interstellar particles and galactic cosmic rays. These energetic particles, forged in supernova events and other violent phenomena, sweep through the galaxy. Most are turned aside or slowed by the magnetic fields carried by the solar wind. Only a small share reaches Earth's orbit, and fewer still slip past Earth's own magnetic field to touch the atmosphere. The shield around us is not flawless. The Sun follows an 11-year rhythm, and its mood shapes the very boundary of our cosmic home. During a solar maximum, when the solar wind grows stronger and the magnetic field swells, the heliosphere pushes outward and blocks more of the cosmic rays drifting in from the galaxy. During a solar minimum, that great bubble contracts and weakens, and more of those high-energy particles slip through. Earth feels the difference. We measure noticeable increases in cosmic ray flux during the quieter phases of the cycle, and the size of the heliosphere shifts as the solar system moves through different interstellar clouds. When we enter a denser region of the interstellar medium, the external pressure rises. It squeezes the heliosphere and pushes the boundary, known as the heliopause, closer to the Sun. In emptier regions, the bubble expands again. Scientists believe the heliopause could shift inward by 20 or 30 astronomical units if we encountered a dense enough cloud, bringing interstellar space far closer to Earth than it is now. If the heliosphere were compressed too much, more cosmic rays would reach our world. More interstellar gas would flow into the inner solar system. That heightened radiation could threaten satellites and spacecraft, and it might even influence the chemistry of our atmosphere. Some researchers propose that large changes in the heliosphere's size could shape Earth's climate over millions of years. The evidence is uncertain, yet one truth remains. The shield that cradles us is alive. It breathes. It bends. Its strength depends entirely on the galactic environment through which we travel. There is a boundary in space where the sun's rule ends. Beyond that boundary, the galaxy itself becomes dominant. Voyager 1 crossed this frontier on the 25th of August in the year 2012. It became the first human machine to enter true interstellar space. The crossing happened at 121 astronomical units from Earth, a distance of roughly 11.3 billion miles. Voyager 1 spent 35 years on that journey. It launched in September 1977, swept past Jupiter and then Saturn, and continued outward, carrying messages from humanity in case it ever encountered another mind among the stars. It no longer had planetary goals. Its purpose was to explore the edge of the sun's influence and reveal what waited beyond. For years before the crossing, its instruments sensed a gradual rise in cosmic rays as the solar wind thinned. The spacecraft was approaching something unknown, and no one could predict the moment of transition. Then in June 2012, Voyager 1 recorded a sudden 9% increase in cosmic ray flux in the span of a single month. The rise continued into July and August. A dramatic boundary lay ahead. On the 25th of August, the spacecraft measured a sharp drop in solar wind particles. The count fell from about 25 particles per second to about 2 particles per second within days. At the same time, galactic cosmic rays surged. The magnetic field direction shifted. Voyager 1 had crossed the heliopause. The sun's influence was over. Interstellar space had begun. Yet something puzzled scientists. The magnetic field beyond the boundary did not rotate as sharply as expected. Theory suggested that inside the heliosphere, the magnetic field carried a specific orientation set by the sun. Outside the field should align with the local interstellar field, shaped by galactic processes. The change was subtle. This hinted that the interstellar magnetic field in that region might share a similar orientation by chance, or that the boundary was more complex than simple models implied with tangled fields and layered transition zones. Voyager 2 crossed the heliopause 6 years later, in November 2018, at a distance of 119 astronomical units. Its measurements confirmed Voyager 1's findings, but also deepened the mysteries. The two crossings happened at different distances, showing that the heliopause is not a smooth sphere. It ripples and shifts with changes in solar wind pressure and the character of the interstellar medium. Both spacecraft still send back data, though their power continues to fade. Their radioisotope thermoelectric generators decay a little more each year. By the late 2025 period or the early 2030s, both Voyagers will likely fall silent as they drift onward into the dark, carrying their golden records with voices, music and sounds from Earth. Beyond the heliopause, the universe changes. Radiation rises. The temperature of the surrounding plasma rises from about 50,000 degrees inside the heliosphere to far hotter levels beyond it. The density of neutral atoms shifts as well. The sun becomes simply another star in the sky. Its gravitational and electromagnetic influence is no longer overwhelming as it is closer in. Yet even at 121 astronomical units, the sun still rules through gravity. The planets remain bound within 50 astronomical units. The Kuiper belt reaches outward to perhaps 100 astronomical units, but gravity stretches far beyond that. The question is not whether the sun's gravity extends past the heliopause. The true question is where that gravity becomes too weak to hold an object in orbit. That frontier where objects become more loyal to the galaxy than to the Sun, lies far beyond the point where Voyager 1 entered interstellar space. That frontier marks the beginning of the region known as the Oort cloud. What waits there makes the heliopause feel like nothing more than a doorway. At that distant boundary, the Sun's influence fades to nothing. Imagine a vast sphere of frozen bodies enveloping our entire solar system. This sphere stretches from about 2,000 astronomical units to roughly 200,000 astronomical units from the Sun. Its diameter spans around 3 light-years, reaching almost halfway to the nearest star. Within this enormous shell, trillions upon trillions of icy fragments drift in darkness. Many are smaller than a city. Some rise to the scale of mountains. This is the Oort cloud, and no one has ever seen a single object within it directly. Its presence is inferred rather than confirmed. We observe comets arriving from every direction as they plunge inward. They do not come from the ecliptic plane where the planets travel. They do not come from the flattened disk of the Kuiper belt. They fall toward the Sun from above, below, and from every side, which suggests a spherical reservoir surrounding us. The equations support this idea. The orbital patterns match it. The cloud almost certainly exists, yet we cannot see it because its objects are too small, too dark, and too remote to reflect enough sunlight for detection. An astronomer proposed this distant cloud in 1950 after examining the orbits of long-period comets. He noticed that these comets took thousands or even millions of years to complete a single orbit and arrived from directions that seemed random. Something had to be disturbing them and sending them inward. He calculated that a spherical cloud of icy remnants at extraordinary distances could explain the observations. The idea endured, and the cloud took his name. Here is what resides in the Oort cloud. It holds material left over from the formation of the solar system around 4.6 billion years ago. When planets formed from the swirling disk of gas and dust around the young Sun, not all material became part of those worlds. Small bodies of rock and ice were cast outward by gravitational encounters with Jupiter, Saturn, Uranus, and Neptune. Some pieces escaped the solar system entirely. Others lacked the speed to break free, but were pushed into distant orbits where they barely remained bound to the Sun. Across billions of years, these objects dispersed into a roughly spherical shell. Gentle pulls from passing stars, the tidal forces of the Milky Way, and countless random encounters gradually reshaped their orbits and spread them evenly around the solar system. This forms the Oort cloud we theorize today. It consists of 2 main regions. The inner Oort cloud, also known as the Hills cloud, extends from roughly 2,000 to 20,000 astronomical units. This region might resemble a thick torus centered around the ecliptic plane. It is denser than the outer cloud and may contain tens or even hundreds of times more objects, though still sparse enough that no 2 bodies are close. Each object drifts alone in the void, separated from its nearest companion by billions of miles. The outer Oort cloud stretches from 20,000 to 200,000 astronomical units. This region forms a true sphere surrounding the solar system from every direction. The objects out there orbit the Sun with immense slowness. A single orbit can take millions of years. Some comets have never completed even one full journey since the cloud formed in the early days of the solar system. Estimates of the total number of objects vary greatly. Conservative views suggest several trillion bodies, larger than about half a mile. More generous ideas reach into the tens of trillions. The total mass might equal a few Earth masses. Some estimates place it at between 5 and 10 Earth masses when counting every fragment down to tiny grains. These values remain uncertain. The objects themselves are untouched relics. They have not been warmed by the Sun since the dawn of the solar system. They hold ice preserved from the original molecular cloud that collapsed to form our star and planets. Studying them would reveal the earliest conditions of our cosmic home, yet we cannot reach them. The fastest spacecraft so far, New Horizons, moves at about 36,000 miles per hour relative to Earth. At that speed, the inner edge of the Oort cloud lies about 5 centuries away. The outer edge is a journey of around 30,000 years. The Oort cloud remains a ghostly presence. We are confident it exists. We feel its influence when comets plunge inward toward the Sunday, yet we cannot touch it or capture a clear image of it. Its structure evades us. It waits at the outer edge of the Sun's gravitational reach. These are the last objects still held by our star before the galaxy asserts full control. And something far out there is stirring it. Something is disturbing those remote orbits and sending comets drifting toward Earth. What kind of force can reach across light years and rattle 1 trillion frozen fragments of ice? The answer lies within the galaxy itself. Between the outer planets and the distant spherical cloud sits a structure predicted in the year 1981. Scientists still cannot observe it directly. It is a ring-shaped population of icy bodies. They are far more densely packed than those in the outer cloud. This is the Hills cloud, named for astronomer Jack Hills. It may explain why comets keep falling toward Earth, even though billions of years should have drained the outer cloud. The issue is straightforward. Objects in the outer cloud orbit so far from the Sun that their gravitational tether is weak. A passing star, even one drifting within a few light years, can tug with enough tidal force to strip comets away or twist their orbits. Over 4.6 billion years, the outer cloud should have thinned dramatically. Random stellar encounters should have scattered most of its contents throughout the galaxy. Yet long-period comets continue to arrive. The supply appears steady. Hills suggested a possible answer. Perhaps a denser reservoir lies closer to the Sun, enclosed within the outer cloud. This inner region would be held more firmly by solar gravity. It would be less vulnerable to passing stars or galactic tides. Objects inside the Hills cloud could endure for billions of years, occasionally pushed outward or inward by subtle gravitational nudges. Computer simulations supported the idea. When scientists modeled the birth of the Oort cloud following icy debris flung outward by planetary encounters, they discovered that many objects did not travel straight into a distant sphere. Instead, they settled into intermediate paths. These paths formed a thick ring aligned with the ecliptic plane. This inner cloud arose naturally from the physics of planetary migration and gravitational scattering. The Hills cloud probably stretches from about 2,000 astronomical units to about 20,000 astronomical units from the Sunday. Its vertical thickness may span several thousand astronomical units above and below the ecliptic. Its density could be tens or even hundreds of times greater than the outer Oort cloud. This suggests that most cometary nuclei in the entire region actually reside within the Hills cloud rather than the more familiar outer shell. Here the story becomes even more intriguing. A recent study released in early 2025 proposed that the Hills cloud might not form a simple ring. The team ran more sophisticated simulations and found that early gravitational encounters with the planets, especially during their migrations, might twist the inner cloud into a spiral. Instead of a smooth torus, the cloud may resemble a loose spiral with density variations depending on angle and distance from the Sunday. Such a spiral would help explain strange patterns in long-period comet data. Comets do not arrive with the perfect uniformity expected from a spherical outer cloud. There are faint directional preferences. These slight anisotropies hint at hidden structure. If the Hills cloud contains spiral features, these features could influence the directions from which comets fall toward the Sunday. The Hills cloud is important because it replenishes the outer Oort cloud. As objects in the outer cloud are stripped by passing stars or stirred by the galaxy, the inner cloud supplies replacements. Without this reservoir, the Oort cloud would have dispersed long ago. Long-period comets would have vanished from the inner solar system billions of years before Earth became habitable, yet the Hills cloud also increases the sensitivity of our solar system to certain disturbances. A star passing within a few light years may not affect it much, but a star drifting within 10,000 to 50,000 astronomical units and moving through or near the inner cloud could scatter enormous numbers of comets at once. Such an encounter could unleash a comet shower. Hundreds or thousands of comets might fall toward the inner planets over a span of a few million years. Has this occurred? It might have. Some researchers propose that periodic comet showers could align with extinction events on Earth. A passing star could disturb the Hills cloud and send swarms of comets inward. Multiple impacts within a short geological window could impose dramatic stress on Earth's climate and biosphere. The idea remains debated, but the underlying physics is solid. The Hills cloud, if it exists as models suggest, leaves our solar system exposed to close encounters with passing stars in a way a smooth and spherical outer cloud would not. Yet no one can confirm its presence because it lies far beyond the reach of spacecraft and far beyond the sensitivity of our telescopes. It remains a theoretical structure sustained by equations and simulations, never by direct observation. It is a kind of unseen fortress that we believe surrounds the outer Oort cloud. But something is disturbing that silent boundary. Something reaches across thousands of astronomical units and stirs those distant frozen worlds. The galaxy itself pulls on those comets. The Milky Way tries to draw the Oort cloud apart. It does this slowly and persistently. The gravity of the galaxy squeezes and stretches the farthest regions of the solar system, altering the orbits of comets at the outer edge of the Sun's influence. This force is known as the galactic tide. It is the main driver of long-period comets that fall toward Earth. Think of the way the Moon raises ocean tides on Earth. The Moon pulls more strongly on the side of Earth nearest to it than on the far side because gravity weakens with distance. This difference stretches Earth slightly. It creates one bulge of water facing the Moon and another on the opposite side. The tides rise and fall as Earth rotates through those bulges. The same principle acts on the Oort cloud, although the force comes from the Milky Way's distribution of mass. Most of the galaxy's visible matter lies in the galactic disk, where stars and gas form a flattened structure. This mass pulls on the solar system. It pulls more strongly on the side of the Oort cloud facing the disk than on the side facing away. The difference creates a tidal force that stretches the cloud. But the galactic tide is not as simple as the ocean tides on Earth. The Milky Way's mass does not sit at a single point as the Moon does for Earth. Matter spreads across the disk, and the solar system circles the galactic center. This motion introduces extra forces. Astronomers describe the galactic tide with two main components. The radial component points toward or away from the galactic center. This force arises because the solar system moves along a curved orbit around the galaxy. Objects in the Oort cloud on the side facing the galactic center feel a slightly stronger inward pull than objects on the far side. The result is a gentle squeeze along the line pointing toward the center of the galaxy. The vertical component points perpendicular to the galactic plane. This force comes from the mass in the galactic disk, drawing objects toward the plane. Comets above the plane feel a downward pull. Comets below the plane feel an upward pull. This component squeezes the cloud along the axis that stands perpendicular to the disk and stretches it along the other two axes. These tidal forces are extremely weak. At Earth's distance from the Sun, the galactic tide has no measurable effect. It is billions of times weaker than the Sun's direct pull. But far out, at 50,000 or 100,000 astronomical units, where Oort cloud comets drift, the Sun's gravity fades dramatically. Out there, the galactic tide becomes similar in strength to the Sun's pull. The two forces compete. The boundary where this competition is decided is known as the tidal truncation radius. It is the distance from the Sun where the galactic tide becomes strong enough to remove objects from the Sun's grip. Beyond this boundary, comets cannot remain bound forever. The tidal force will strip them away and send them into interstellar space. The tidal truncation radius lies somewhere between 100,000 and 200,000 astronomical units. It marks the true outer edge of the Oort cloud. Here is how the galactic tide drives comets toward Earth. Imagine a comet drifting in the outer cloud with a nearly circular orbit at about 50,000 astronomical units. The galactic tide tugs on the comet over millions of years, altering its orbit bit by bit. Sometimes these small changes increase its orbital energy and push it outward toward the tidal truncation radius, where escape becomes possible. But other times the changes reduce its orbital energy, stretching its orbit into a long ellipse. If the ellipse grows extreme enough, the comet's closest approach to the Sun drops below a few dozen astronomical units. It then enters the realm of the giant planets. Jupiter, Saturn, Uranus and Neptune can now interact with it through gravity. They can scatter it outward into interstellar space, or send it inward on a shorter orbit that carries it into the inner solar system where it becomes visible. The galactic tide is not the only influence. Passing stars also disturb cometary orbits. Giant molecular clouds containing hundreds of thousands of solar masses drift through the galaxy. They sometimes pass within a few hundred light years of the solar system and exert tidal forces of their own. But the galactic tide is constant. It does not rest. It always pulls and always reshapes the cloud. Calculations show that the galactic tide alone can account for most of the long-period comets we see. About half of the comets that enter the inner solar system likely do so because of these tidal perturbations, rather than because of passing stars. The galaxy reaches across light years of space and stirs ancient ice at the edge of the solar system, sending it inward toward the Sun. This slow process has unfolded for billions of years. It will continue for billions more. The galaxy waits. The galaxy never stops pulling, and most of the Milky Way remains invisible. The stars, we see the gas and the dust, represent only about 15% of the total mass of the galaxy. The rest is dark matter, and it surrounds the entire galaxy in a vast halo that reaches hundreds of thousands of light years into space. Dark matter does not shine. It does not dim incoming light. It does not respond to electromagnetic radiation in any way that scientists can detect. It reveals itself only through the pull of gravity. Astronomers uncovered its presence by measuring the speeds of stars orbiting around galactic centers. Those stars move far too quickly. If galaxies contained only the matter we can see, then stars in the outer regions should orbit more slowly. Outer planets in our solar system move slowly because they feel weaker gravity. Yet the stars refuse to slow down. Galaxies spin almost like solid disks, with outer stars racing nearly as fast as stars close to the center. The only reasonable conclusion is that galaxies contain far more mass than what our eyes and telescopes can detect. This hidden mass forms a great halo around the visible disk. It provides the extra gravity needed to keep stars bound at their observed speeds without drifting off into intergalactic space. The dark matter halo of the Milky Way is immense. Computer models suggest it stretches at least 600,000 light years from the core, and perhaps even farther. Its total mass might exceed the mass of all visible stars, gas and dust by a factor of 10. The halo is not empty. It is filled with dark matter particles. These particles are abundant enough to hold the galaxy together, but sparse enough that their density remains extremely low. This is where it touches the solar system. The dark matter halo contributes to the galactic tide acting on the cloud of icy bodies at the solar system's edge. When scientists calculate the tidal forces stretching and squeezing that distant region, they include two main sources. One source is the visible matter in the galactic disk, all the stars and gas we can observe directly. The other source is the dark matter halo. Its contribution adds about 15% to the total galactic tide. That may seem small, but at the distance of the cloud where gravitational forces are faint, 15% makes a difference. It means comets shift their orbits slightly faster than they would if only visible matter existed. The timescale for orbital change shortens. The rate at which comets fall inward increases. Some researchers have proposed that if the local density of dark matter is high enough, we might detect it directly within the solar system. The idea is that dark matter particles, although invisible to light, might interact weakly with normal matter. Rare collisions between dark matter particles and atomic nuclei in Earth-based detectors could produce detectable signals. None has been confirmed so far, despite decades of increasingly sensitive experiments. These silent results impose strong limits on the ways dark matter can interact with ordinary matter. Either dark matter interacts even more faintly than expected, or it consists of something more exotic than current theories propose. Yet dark matter must exist. The evidence written in gravity is overwhelming. Galaxies would tear themselves apart without it. Clusters of galaxies would drift away. The cosmic web of galaxies and voids would fail to form in simulations without dark matter acting as a gravitational framework. Something unseen shapes the universe, and we call it dark matter, even though its nature remains unknown. For the cloud at the edge of our solar system, what matters is that this invisible halo contributes to the forces tugging at distant comets. Dark matter cannot be ignored when calculating orbital dynamics near the boundary of the solar system. It changes how quickly the galactic tide stirs cometary orbits. It shifts the location of the tidal truncation radius. It helps define the border between what remains gravitationally bound to the Sun and what is lost to the galaxy. Recent studies offer an even stranger possibility. The dark matter halo may not be smooth. It may contain smaller clumps and flowing streams of dark matter drifting through the galaxy. If one of these clumps passed through the cloud, it could scatter comets far more strongly than the smooth halo. Such an encounter might unleash a storm of comets, sending thousands of them toward the inner solar system within a geologically brief moment. Has this occurred? We do not know. Evidence for dark matter substructure is still uncertain, and spotting such an event in Earth's geological layers would be extremely difficult. But the possibility remains. The halo surrounding us may not be a gentle and uniform sea. It may contain structures, features, perhaps even sharp density spikes called caustics. If one of these features sweeps through our region, it could jolt the cloud in ways unseen for billions of years. Hidden within the halo of the Milky Way are boundaries where density rises by orders of magnitude. These boundaries are known as caustics, and they form naturally when cold dark matter collapses into a galaxy. Caustics exist as surfaces in three-dimensional space, places where dark matter flowing from many directions converges and piles up. If such a surface passes through the solar system, it could scatter comets in the cloud with far greater force than the smooth background halo. Here is how caustics arise. When the Milky Way first took shape billions of years ago, dark matter fell inward from every direction. This inward fall was not smooth. Dark matter streamed through the cosmos in graceful flows that converged from many directions. Where these flows met, the density rose sharply. The streams did not pass through one another because dark matter behaves as a collisionless medium. Instead, they gathered at the crossing points and formed delicate sheets of heightened density. These sheets are known as caustics. The term comes from optics, where caustics describe patterns of concentrated light, like the bright shifting lines on the floor of a swimming pool when sunlight bends through moving water. In the case of dark matter, caustics mark places where gravity brings the dark material into focus. The density inside a caustic can rise by a factor of 10, 100, or even 1000 compared with the surrounding halo. These structures form rings that lie within the galactic plane. The first ring sits closest to the heart of the galaxy, at a distance of roughly 10,000 light-years. Each ring lies farther out than the one before. The fifth ring might reside near 27,000 light-years from the center, close to the position of the Sunday. Some studies suggested that we may currently drift within that fifth ring, traveling through a region of amplified dark matter density. If this idea is correct, it carries weighty implications. The dark matter around us would be higher than average, which might make detectors on Earth more likely to sense a faint signal. The gravitational influence on the distant Oort cloud would also grow stronger. If the orbit of the solar system moves in and out of the ring over spans of millions of years, then the disturbances that dark matter creates in the Oort cloud would rise and fall through time. Yet caustics do not remain fixed. They drift outward over the long evolution of the galaxy. A moving ring passing through the solar system would generate a temporary rise in dark matter density that could last a few 100,000 years as the ring glides past. During such an interval, the extra gravitational pull could jostle Oort cloud comets more strongly than usual. Researchers calculated the possible outcomes of a caustic passing through that distant reservoir. The increased density would tug on cometary orbits and shift them slightly. Most comets would feel only subtle changes because dark matter, even in a caustic, remains extremely diffuse. But near the outer edge of the cloud, where the grip of gravity is already weak, the added pull might tip a few comets into paths that send them toward the inner solar system. The likelihood of a noticeable effect is small, perhaps 0.003%, yet it is not zero. If caustics sweep through the solar system every few tens of millions of years, then at least once or twice in the long history of Earth, a passing ring may have raised the number of comet impacts. Whether this ever happened and whether any trace of it survives in the geological record remains unknown. The very existence of caustics is still debated. Their prediction arises from simulations of cold, dark matter halos, and certain patterns in the motions of stars in the Milky Way hint that caustic-like structures may be present. But direct confirmation has not arrived from dark matter detection experiments. If dark matter is not made of cold, collisionless particles, these structures may never form. The sharpness of caustics makes them especially fascinating. The broader dark matter halo changes density slowly across thousands of light years, but a caustic is a thin boundary only a few light years thick, where density rises abruptly. Crossing such a boundary would feel like moving through a sudden shift in the gravitational environment. For the Oort cloud, it would mark the entrance into a region where dark matter tides grow stronger for as long as the solar system remains within the sheet. No one knows whether we approach a caustic now, drift away from one, or lie far from any such structure. The uncertainties in the orbit of the solar system and in the predicted locations of the rings are simply too large. We could pass through a caustic tomorrow, or we might avoid one for 100 million years. The dark matter halo hides its secrets well. It pulls on everything around it, silently and steadfastly, while its densest regions remain concealed in darkness. Above and below the galactic plane, beyond the thin disk of stars, space fills with a vast cloud of gas, heated to temperatures that would destroy any solid in an instant. This is the halo of hot galactic gas, a diffuse plasma stretching across hundreds of thousands of light years and glowing softly in X-rays. Its temperature reaches 1 million degrees Kelvin or more, high enough to strip electrons from atoms and create a sea of charged particles that weave intricate patterns with magnetic fields. This hot halo is different from the dark matter halo. Dark matter is invisible and extends even farther into space. The hot halo is ordinary matter made mostly of hydrogen and helium, with small traces of heavier elements. But it is so hot and so thin that it produces almost no visible light. Only X-ray observatories can reveal it by detecting the energetic photons released when electrons in the plasma slow down or drop between energy levels in ionized atoms. The mass of this hot halo is immense. This gas accounts for much of the galaxy's missing baryonic matter, the ordinary matter that theory predicted for decades, but astronomers could not locate. They searched in the wrong wavelength. The gas is far too hot to shine in visible light. You need X-ray vision to reveal it. The heat comes from two main sources. One source is the blast of supernova events. Explosions in the galactic disk hurl immense energy into the surrounding gas. Shock waves from these explosions raise the gas to millions of degrees and drive it upward into the halo. Astronomers call this a galactic fountain. Hot gas rises, cools as it travels and then falls back toward the disk under gravity. It heats again and is thrown upward once more. The cycle never stops. The second source is gravitational energy. As the Milky Way formed, gas fell inward and converted gravitational potential energy into motion and heat. This accretion heating lifted gas temperatures to millions of degrees. Even now, the galaxy continues to pull in gas from the intergalactic medium, and this new material heats as it drops into the galaxy's gravitational well. The hot halo is not smooth. It has structure. Temperature and density shift from place to place. Near the galactic plane, where supernova explosions are common, the gas is hotter and more chaotic. Higher above or below the plane, the gas cools slightly and becomes gentler. Yet, everywhere, the temperature remains above a few 100,000 degrees. The gas stays ionized and remains invisible to ordinary optical telescopes. Recent X-ray studies revealed vast bubbles in the halo, stretching thousands of light years above and below the galactic center. These bubbles, detected by the Reuter telescope, appear to be shock-heated zones born from past activity in the Milky Way's central black hole. Millions of years ago, perhaps 10 million years ago, that black hole may have been far more active, swallowing matter and firing jets of energy perpendicular to the galactic plane. These jets inflated colossal bubbles in the halo gas. Their remnants still linger. The hot halo interacts with everything that moves through it. High-velocity clouds of cold gas falling toward the galaxy carve shock fronts as they plow through the hot medium. Stellar streams, long trails of stars, drawn from disrupted satellite galaxies, drift through the halo and feel drag from the thin gas. Even the solar system touches the halo, though we sit too close to the galactic plane to feel strong effects from the hottest regions. Far above or below the galactic plane, the hot halo dominates. Globular clusters, ancient spheres of stars, glide through this million-degree plasma without pause. Dwarf galaxies on the edge of the Milky Way feel ram pressure as they move through the halo gas. Their own gas strips away and trails behind them like a comet tail. The halo gas holds metals elements heavier than helium. Stars forge these metals through nuclear fusion and release them when they exploded as supernova events or shed their outer layers in stellar winds. The metals in the halo prove that material from the disk travels outward into the halo and spreads enriched matter across the galaxy's vertical reach. Scientists estimate that this gas will stay hot for billions of years. Cooling processes exist, but act slowly in such thin environments. The gas radiates energy as X-rays, but the cooling timescale exceeds the age of the universe in most regions. Only near the denser zones of the galactic plane does gas cool enough to fall back and replenish the disk. This hot halo offers part of the answer to what lies above and below the solar system. Travel far enough in either direction, and you leave the familiar expanse of stars and enter a realm shaped by invisible dark matter and hot glowing plasma. A realm where temperatures soar but densities fall so low that you could journey for light years without gathering enough atoms to fill a thimble. A realm where the rules shift and the true design of the galaxy emerges. In December 2020, astronomers using the EROSA X-ray telescope uncovered a startling sight. Two gigantic bubbles rise 14,000 light-years above and below the galactic center. 14,000 light-years. That span equals half the radius of the Milky Way's visible disk. These bubbles radiate X-ray light, invisible to human eyes, marking regions where gas was shocked and heated beyond 2 million degrees. The bubbles stand nearly symmetrical. One lies above the plane. One lies below. Their edges cut sharply through space, tracing collisionless shocks formed where hot gas slams into cooler surroundings. The southern bubble contains a structure that puzzled astronomers for decades. It is called the North Pole Spur, a vast arc of radio and X-ray emission visible from Earth's northern hemisphere. No one realized until Eroita that the North Pole Spur is one boundary of a galaxy-scale bubble. What force created such vast shapes? Two possibilities remain: a surge of star formation in the galactic center, or activity from the supermassive black hole. Both can supply enough energy to inflate bubbles of this scale. Scientists estimate the total energy required equals about 100,000 supernova explosions occurring over a short time, or 1 million solar masses of matter falling into the central black hole and converting part of that mass into radiation and motion. The timing reaches back millions of years, perhaps between 10 and 20 million years. The bubbles no longer surge outward with great speed. They drift instead, moving slowly in the late stages of their evolution. The shock fronts along their edges have weakened compared with their fierce beginnings, yet the structure endures. It stretches across thousands of light years and marks one of the most violent episodes in the recent history of the Milky Way. The bubbles shape everything they touch. High-velocity clouds that pass too close are pushed or torn apart by the shock fronts. Magnetic fields in the galactic halo are pressed and strengthened along the expanding walls. Cosmic rays, those high-energy particles driven by the shocks, flow along the bubble rims and travel outward into space. Some of them may one day reach Earth. Scientists compared the X-ray bubbles with structures observed in other wavelengths. Gamma-ray telescopes had already found similar features, known as the Fermi bubbles, named after the Fermi Gamma-ray Space Telescope. The Fermi bubbles align almost perfectly with the Arosa X-ray bubbles, showing they are the same structures seen in different forms of light. Radio telescopes also detect emission from the bubble regions and reveal magnetic fields and relativistic particles. What gives the discovery its weight is the scale. These are not nearby oddities. These are vast galactic structures that show the Milky Way's central region can unleash outbursts powerful enough to influence the entire halo. If you lived on a world inside a star cluster above the galactic plane immersed within one of these bubbles, your sky would blaze with radiation from shock-heated gas. Life would endure challenges Earth has never known. The bubbles also carry clues to the past of the galactic center. The Milky Way's central black hole is quiet today. It draws in material slowly and produces little radiation when compared with active galactic nuclei in other galaxies. But the bubbles show that it was not always silent. At some point, within the last 10 million years, something fed the black hole. A cloud of gas may have fallen inward. Stars may have wandered too close and been torn apart. Or a small galaxy may have merged with the Milky Way's core. Whatever occurred released enough power to drive gas 10,000 light-years above the plane. The violence was extreme, the energy was immense, and the evidence still shines above and below us, marking the place where the heart of our galaxy erupted. The bubbles will eventually fade as the gas cools and spreads, but for now they stand as giant scars in the halo traces of an ancient upheaval. For 70 years, astronomers debated a great arc of radio and X-ray emission stretching across the northern sky. Some believed it was the remnant of a nearby supernova a few hundred light-years away. Others insisted it was a distant galactic structure thousands of light-years from Earth. No consensus emerged. The feature became known as the North Pole Spur, and it dominated the radio sky above the galactic plane. The spur covers more than 100 degrees when viewed from Earth. That size could point to a small nearby object or to a huge distant structure. Measuring its distance was impossible because the spur contains no stars or other objects with measurable parallax. It is only gas-emitting radio waves and X-rays with no markers to reveal how far away it lies. Some researchers favoured a local supernova. They calculated that a star exploding around 30,000 to 100,000 years ago at a distance of a few hundred light-years could launch a shockwave large enough to appear across that portion of the sky. The X-ray glow would arise from shock-heated gas. Others raised clear objections. The required energy seemed too high for one nearby supernova. The structure looked too orderly and too smooth. Its orientation aligned too neatly with the galactic plane, rather than pointing in a random direction as a local remnant should. These scientists argued that the North Pole Spur must belong to a larger galactic structure linked to the Milky Way's central activity or to major features in the halo. The Arecibo telescope resolved the argument in the year 2020. The full sky X-ray map showed that the North Pole Spur is the southern edge of a colossal bubble, rising 14,000 light-years above the galactic center. The spur is not a separate object. It is part of the Arosa bubbles described earlier. The mystery dissolved when the wider view came into focus. What seemed like a local feature was revealed as a distant galaxy-scale structure. The confusion arose because the southern edge of the northern bubble points roughly toward Earth. When we look north from our position slightly above the galactic plane, we see the bubble's shock front edge on. That view appears as the North Pole Spur. The rest of the bubble stretches away from us and is harder to see because we observe it face on rather than along its rim. The discovery ended decades of debate. The North Pole spur appears to trace a moment of profound energy released from the heart of our galaxy many millions of years in the past. Its source lies around 25,000 light-years from us, near the galactic center. Yet the spur itself stands closer because it marks the near boundary of an enormous expanding structure. The driving force was likely a burst of rapid star formation or a phase of black hole activity. Either one can deliver the immense power needed to inflate bubbles of this scale. But the story turns in an unexpected way. In the southern sky, there is a matching feature known as the South Polar Spur. It is harder to see from the northern hemisphere of Earth, yet it rises as part of the Irisita bubble that stretches below the galactic plane. Together, the two spurs sketch the edges of a giant bipolar outflow driven from the core of the Milky Way. Solving the puzzle of the North Pole spur shows how challenging it is to measure distances to faint and diffuse formations in space. When astronomers lack reliable markers such as stellar parallax or standard candles, they must depend on shape energy demands and links to nearby structures. Sometimes clarity arrives only when a more advanced telescope uncovers the wider scene. For Earth, the true identity of the North Pole spur means we are not sitting inside a nearby supernova remnant. We are simply observing the rim of a vast structure from our position within the galaxy. Its radiation reaches us only in a diluted form across great distances and poses no danger. Yet this immense formation reminds us that the galactic center can erupt with astonishing violence. It can send waves of energy and radiation across thousands of light years. Our galaxy is a living and changing system. The calm we witness today is not promised to remain. Above and below the Milky Way, like two great rings stacked on either side of the galactic plane, lie invisible magnetic field structures. These fields follow the motion of the galaxy, forming toroidal patterns in which the lines of force wrap around the galactic center in looping paths. In the northern toroid, the field points in one direction. In the southern toroid, it points the other way. This contrast reveals something essential about the way galaxies generate magnetic fields. A magnetic field emerges from the movement of charged particles. In galaxies, rotation and convective flows in ionized gas create a dynamo effect. It mirrors the process inside Earth, where the liquid ion core sustains our planet's magnetic field. The galactic version stretches across thousands of light years, yet the principle is the same. Moving plasma twists and strengthens magnetic fields until they reach a steady state. The toroidal halo fields rise above and below the disk of the galaxy for perhaps 1,000 to 2,000 light years. They stand apart from the fields within the disk, although the two regions must link in ways not yet fully clear. Finding those connections is a difficult task, because mapping three-dimensional magnetic structures from our vantage point inside the galaxy is extraordinarily challenging. Scientists detect these halo fields through several lines of evidence. Polarized radio waves from faraway sources rotate as they travel through magnetized plasma. This effect, called Faraday rotation, reveals details about the strength and direction of magnetic fields along the path. By measuring this rotation toward many thousands of sources, astronomers piece together the structure of the galactic magnetic field. The observations show a striking pattern. When we look north toward the galactic pole, the rotation points to fields directed one way around the galaxy. When we look south, the rotation points the opposite direction. This north-south contrast is the hallmark of toroidal fields with reversed orientations in each hemisphere. The fields in the halo are weaker than the fields in the disk. The disk may reach between 5 and 10 microgauss. The halo may range from 1 to 3 microgauss. 1 microgauss is 1/1,000,000th of a Gauss. At Earth's surface, the planetary field is around 1/2 Gauss. Galactic fields are incredibly faint by everyday experience. Yet stretched across thousands of light years, even such delicate fields can shape the motion of charged particles and cosmic rays. The toroidal fields confine cosmic rays. These high-energy particles, often born from supernova explosions and other violent events, cannot easily cross magnetic field lines. They spiral around them and remain held in the halo for long spans of time before drifting into intergalactic space. This extra confinement raises their density and increases the likelihood they will collide with gas or eventually find their way to Earth. Recent models propose that the halo fields may extend far more than once believed. Rather than ending at 1,000 or 2,000 light years, they might reach 10,000 light years or more, occupying much of the region filled by the Erossiter bubbles. The magnetic fields would press and strengthen along the advancing shock fronts of the bubbles. The presence of such ordered magnetic patterns across galactic scales came as a surprise. Turbulence in the interstellar medium should twist field lines into chaotic knots. Yet observations reveal structures of remarkable coherence stretching across thousands of light years. The galactic dynamo must be far more adept at imposing order than early theories suggested. For matter in the galactic halo, these magnetic fields play a vital role. Cosmic rays stream along the lines of force. Charged particles feel sideways pushes that cause them to drift around the galaxy. Even neutral gas can sense magnetic influence if a fraction of it is ionized with magnetic tension and pressure guiding its motion. And these fields never remain fixed. They change as the galaxy turns and as new dynamo currents create fresh magnetic fields. Simulations hint that these great toroidal structures may reverse over billions of years, with the northern field becoming the southern field and the southern field becoming the northern. We may be witnessing only one brief moment in a magnetic cycle that spans cosmic time. The unseen magnetic rings above and below us act as part of the vast galactic engine that shapes the halo. They steer particles. They hold energy. They link the disk to the halo in ways gravity cannot achieve alone. You cannot see them, you cannot sense them, yet they are there, wrapping the galaxy in an electromagnetic architecture. Scattered across the regions above and below the galactic plane lie ancient spheres of stars known as globular clusters. Each cluster holds hundreds of thousands to millions of stars pressed into a compact ball only tens of light years wide. They trace long paths through the halo, rising high above the disk and then descending again, crossing the plane every few 100 million years. Some move clockwise around the galaxy, others move counterclockwise, traveling against the rotation of the disk. They rank among the oldest structures in the Milky Way. Globular clusters formed more than 10 billion years ago, in an age when the Milky Way was still taking shape. Their stars contain very few heavy elements when compared to the Sun, because they were born before waves of supernovae enriched the galaxy. These population 2 stars are ancient witnesses from the youth of the Milky Way, still shining quietly in the halo. Around 150 clusters orbit our galaxy. Most remain within 100,000 light years of the center, but a few travel far beyond. The most distant known cluster circles at more than 200,000 light years, well outside the visible disk, deep in the dark matter halo, linked to the galaxy by gravity alone. At such distances, a single orbit may take several billion years. Their paths do not lie in the galactic plane. Instead, they tilt at many angles, crossing the plane twice per orbit, while spending most of their journey above or below it. This pattern differs completely from the disk stars, which travel almost entirely within the plane. Globular clusters belong to the halo population born before the disk settled into its present flattened shape. About 40% of them move in retrograde orbits. They travel opposite to the rotation of the disk. This backward motion is unusual because the disk stars all move prograde, shaped by the collapse of a rotating cloud of gas. Retrograde paths hint at a different history. Many such clusters likely formed in smaller galaxies that the Milky Way absorbed and destroyed billions of years ago. The clusters endured while their host galaxies were torn apart by tidal forces. Their orbits are not simple ellipses. The galaxy's gravitational field is shaped by the disk, the bulge, and the dark matter halo, each pulling in different ways, depending on position. As a result, cluster orbits precess and wobble, sometimes quite dramatically. A cluster may drift along a rosette path that never repeats in perfect detail. Along these orbits, clusters encounter very different environments. When they cross the plane, they dive through denser regions filled with gas, dust, and stars. Encounters with giant molecular clouds can disturb them, peeling away outer stars and slowly wearing them down across billions of years. Some clusters carry tidal tails. These are streams of stars drawn out along their orbits, marking the slow work of the galaxy's gravity. Far above or below the plane, the halo offers a different setting. The density falls sharply. Stars grow rare. Gas becomes hot and thin. The clusters move through the million-degree halo plasma at hundreds of miles per second, feeling a faint pressure as they push through the diffuse gas. The force is slight, but over immense spans of time, even slight forces can shape their evolution. Scientists turn to globular clusters to study the early Milky Way. These clusters store clues about the galaxy's beginnings in the chemistry and motions of their ancient stars. By measuring their ages, their compositions, and their orbits, astronomers piece together the history of the galaxy's formation. They ask which clusters were born inside the Milky Way and which arrived from captured satellites. The answers help reveal the timeline of galactic growth. Some clusters are fading. They lose stars through evaporation. Random gravitational encounters inside the cluster can give a star enough energy to escape. The star drifts away and reduces the total mass of the cluster. Over billions of years, this process can erase a cluster, completely leaving its stars spread out as a faint stream across the halo. The clusters we see now are the ones that survived. Many others likely lived in the early Milky Way but dissolved long ago. The survivors remain because they are massive enough or distant enough from the galactic center to resist the tearing pull of tidal forces. They will keep circling for billions of years. They drift through the halo as ancient relics of a turbulent childhood. Across that halo, long and delicate streaks of stars stretch out like strands of cosmic pasta. These stellar streams reveal the death places of dwarf galaxies and globular clusters that wandered too close to the Milky Way. Tidal forces drew them apart. Stars were lifted from the front and the back of each doomed system. What remained were rivers of stars flowing around the galaxy, following the final paths of their parent bodies. The most famous example is the Sagittarius stream. The Sagittarius dwarf elliptical galaxy is being pulled apart by the Milky Way right now. As it travels around our galaxy, gravity from the Milky Way tugs harder on the side nearest to us. This difference in gravitational pull stretches the dwarf along its orbit. Stars are peeled away from both ends and form a stream that wraps completely around the Milky Way. The Sagittarius stream spans more than 360 degrees across the sky. It rises above the galactic plane, dives through it, drops below it, then passes through again. If our eyes were sensitive enough, we would see it as a soft band of light encircling the entire sky. But the stars are faint and scattered. Only vast surveys that map millions of stars can reveal its shape. Many such streams have now been identified in the halo. Each one tells the tale of a shattered system. The GD1 stream traces the remains of a globular cluster that no longer exists. The orphan stream has no known parent at all. Whatever formed it has vanished. The Helm stream records a dwarf galaxy merger that happened billions of years ago. New streams keep appearing as surveys grow more sensitive and expand their coverage. These structures are precious because they allow us to follow the Milky Way's gravitational field. Every star in a stream moves along an orbit shaped by the mass of the galaxy. By tracking where these stars lie and how they travel, astronomers can reconstruct the gravitational landscape they explore. This method reveals clues about dark matter. Most of the Milky Way's mass is dark matter, and streams respond to its pull even though it remains invisible. Some streams display gaps or bunches, small fluctuations in their density. These patterns may point to dark matter subhalos. These are small clumps of dark matter that pass through a stream and disturb it. If confirmed, they would offer rare evidence for how dark matter forms structure on small scales and how it flows through the halo. Streams appear mostly in the halo because disruption occurs when objects orbit through these outer regions. Anything in the disk would blend into the billions of disk stars, making streams impossible to detect. But in the halo, where stars are sparse streams, reveal themselves as thin, linear disturbances in a quiet and roughly spherical background. Streams above and below the galactic plane move through environments very different from those inside the disk. They pass through hot halo gas, weave through magnetic fields, and plunge through the dark matter halo. Their paths can take them far from the plane, sometimes hundreds of thousands of light years out, before they fall back and cross the plane again. Each passage exposes them to new conditions. Building a stream is not quick. A dwarf galaxy does not fall apart in one orbit. It can endure many orbits, losing small amounts of mass each time it swings close to the Milky Way's center, where tidal forces are strongest. Older streams are more diffuse. Their stars spread so widely that they become hard to find. Younger streams remain narrow and ordered and easier to detect. Not every stream comes from destruction. Some may be birth streams, loose groups of stars that formed together and stayed associated as they travel around the galaxy. These are difficult to separate from tidal streams unless we know stellar ages and compositions. Birth streams would contain stars of the same age. Tidal streams would carry stars of many ages because their parent systems formed stars across long stretches of time. These streams show that the Milky Way is a cosmic predator. Our galaxy grew by consuming smaller galaxies across billions of years. The streams are what remains, the skeletal traces of what once orbited freely. They pass through the halo in silent arcs of light, witnesses to ancient violence. And the process continues. The Milky Way is still feeding today. New streams will form. The feast will go on. Many dwarf galaxies orbit around us, like moons around a planet. Most contain only millions of stars, tiny compared to the hundreds of billions in the Milky Way. They are small and fragile, yet their arrangement is strange. Instead of forming a roughly spherical cloud around us, as theory once proposed, they lie in a thin plane that cuts across the Milky Way's disk. This vast structure of satellites, often described as a disk, stretches about 600,000 light years from end to end, yet it rises only about 30,000 light years in thickness. It stands almost upright when compared with the Milky Way's stellar disk. Around half of the known satellite galaxies move within this narrow sheet of space, drifting in roughly the same direction. The odds of such an arrangement forming by chance are astonishingly small. When this pattern first appeared in the data during the 1970s, many astronomers dismissed it. At that time, only a handful of satellites had been detected and the sample seemed far too limited. Yet as more dwarf galaxies were found, the pattern held firm. The satellites do indeed gather into a plane, and that plane truly sits at right angles to the disk of the Milky Way. This behavior stands at odds with expectations. In the standard picture of galaxy formation, satellites should orbit in all directions, scattered randomly around their parent galaxy. Their paths ought to reflect the turbulent collisions and interactions that sculpted the Milky Way over billions of years. A thin plane, especially one that rises perpendicular to the disk, hints at some guiding influence. Something shaped their motions, and we do not know what. Several ideas attempt to make sense of this mystery. One proposal imagines the satellites as fragments of a once larger galaxy that the Milky Way tore apart in the distant past. These remnants would continue to follow orbits similar to the path of the original system, forming a plane without any need for exotic physics. Another idea points to a cosmic filament, a great river of dark matter stretching across intergalactic space. If dwarf galaxies fell into the Milky Way along such a filament, they would inherit similar orbital directions, naturally settling into a plane. A third theory turns to the Milky Way's dark matter halo. Recent studies suggest that the halo may not be spherical. It may be stretched like a football or an egg. If that elongated shape stands perpendicular to the disk satellites, passing through that region would feel a different gravitational influence than satellites moving elsewhere. Across billions of years, this could favor the survival of satellites in the perpendicular plane while disrupting others. The most intriguing feature is the coherent rotation. The satellites do not merely sit inside the plane, they orbit around it, and most share the same sense of direction. This implies a collective spin, a system-wide angular momentum, yet a random infall should generate no net rotation. Satellites should move both clockwise and anti-clockwise in equal measure. The puzzle grows when we look beyond the Milky Way. Andromeda also hosts a satellite plane. Several other galaxies do as well. This suggests that such structures may be common. They may emerge from cosmic processes we still struggle to understand. Some simulations now begin to generate planar satellite systems under certain conditions, though the match with what we observe remains incomplete. For our own galaxy, the satellite plane reaches far above and below the disk. If you travelled upward from the solar system along a line perpendicular to the disk, you would not meet this plane for tens of thousands of light years. But if you move sideways along a different perpendicular path, you would cross it much sooner because it slices through space along another dimension. These satellites are slowly dying. Tidal forces from the Milky Way peel them apart over immense periods. Their outer stars drift away, forming streams that trace their former orbits. In time, each satellite will vanish, its stars merging into the halo of the Milky Way. The plane will fade as its members disperse. Yet for now, it endures a mysterious ring of dwarf galaxies circling us in defiance of easy explanation. The dark matter halo around the Milky Way may not line up with the disk at all. New evidence suggests that the halo might be tilted, perhaps even standing perpendicular to the stellar disk. If true, some great event must have reshaped the galaxy. A shift in the orientation of the dark matter while the stars continued to spin in their original plane. Something powerful twisted the halo. Clues come from several directions. The motions of halo stars do not match what we expect from a spherical or disk-aligned halo. Instead, they behave as if responding to a gravitational field that leans away from the disk. The orbits of satellite galaxies show similar signs. The gravitational environment they move through does not appear symmetric around the axis of the disk. Simulations show that tilted halos can form when a large galaxy merges with the Milky Way. Such a collision deposits angular momentum in a new direction. The dark matter, which provides most of the galaxy's mass, slowly adjusts its orientation. The stellar disk, being far lighter, remains largely fixed. The halo then twists and precesses over billions of years until it settles into a new alignment. Some scientists have suggested that the Sagittarius dwarf galaxy may have driven this transformation. Sagittarius has circled the Milky Way for billions of years, plunging through the disk again and again. Each plunge transfers energy and angular momentum into the halo. Over time, this repeated influence could tilt the dark matter distribution. A tilted halo offers explanations for several puzzles. The satellite plane perpendicular to the disk becomes more plausible if the halo itself stands in that direction, because satellites respond mainly to the gravity of dark matter. Even the behavior of certain stellar streams, whose paths do not fit a disk-aligned halo, matches better with this tilted picture. Yet the idea remains unsettled. We sit inside the galaxy, and that makes it extraordinarily difficult to measure the shape and orientation of its dark matter. Dark matter emits no light, so we infer its nature through the gentle pull it exerts on stars and clouds of gas. Those gravitational signatures are faint. They demand measurements of stellar positions and motions with extraordinary precision across great stretches of the halo. Recent studies point to a tilt that began around 6 to 8 billion years ago, roughly halfway through the life of the Milky Way. Before that moment, the disk and the halo lay in harmony. Then something changed. The disk began to lean as well, though, at a slower pace. Deep inside the galaxy where gravity binds stars tightly, some alignment endured. Farther out, the tilt became stronger. If the halo now stands tipped in a direction perpendicular to the disk, our picture of the galaxy must shift. We can no longer assume shared symmetry between these two vast components. Forces acting above and below the disk would differ from those acting sideways. The gravitational landscape grows richer and more intricate. Objects traveling through this tilted halo feel disturbances that defy simple expectations. Even the distant Oort cloud becomes vulnerable. A tilted dark matter halo may shape the long-term stability of comet orbits at the edge of the solar system. Those comets move within a combined gravitational field shaped by both disk and halo. If those two structures point along different axes, the resulting force varies from place to place. Some comet paths may become steadier, others may become fragile. The consequences remain uncertain. If the halo is truly warped, it reminds us that galaxies are restless creations. The stars reveal only part of the story. The dark matter can twist and evolve on its own, shaped by ancient collisions and encounters across billions of years, forming arrangements that appear improbable yet arise naturally from gravity over cosmic time. The galactic disk is not sealed. Gas and energy constantly leak upward and downward, hurled out by the fury of star-forming regions. When several supernovae erupt within a few million years in the same area, they inflate superbubbles that can punch through the surface of the disk. Once the bubble opens, a channel hot gas pours into the halo, like molten rock escaping a crater. Astronomers call these flows galactic winds or chimneys. They lift material thousands of light years above and below the galactic plane. The process begins in nurseries of rapid star birth. Dozens or even hundreds of massive stars emerge from one giant molecular cloud. Their powerful stellar winds sweep gas outward at thousands of miles per second. Within a few million years, the most massive among them explode as supernovae. Each explosion feeds energy into the expanding cavity carved by those winds. The bubble swells. It pushes aside surrounding gas, gathering it into a dense outer shell. If the bubble sits near the midline of the galactic plane where gas is thickest, the shell slows and eventually halts, trapping the bubble in the disk. But if the bubble forms slightly above or below that midline, or if several bubbles merge, the structure can rise. It behaves like a hot air balloon, lifting itself through cooler, denser gas. As it climbs, resistance fades. Gas density falls exponentially with height. What began as a slow ascent turns into a breakthrough. The bubble pierces the upper boundary of the disk and bursts into the thin halo. Hot gas streams outward at hundreds or thousands of miles per second, carrying metals forged in the stars that powered the bubble. These chimneys appear in radio and X-ray observations as tall vertical columns stretching from the disk into the halo. The gas within them is hot and ionized. It is filled with elements heavier than helium, including oxygen, carbon, nitrogen, and iron. Without this transport mechanism, metals would stay locked in the disk. The halo would remain almost untouched, made only of hydrogen and helium from the Big Bang. Yet observations show metals in the halo. Not as many as in the disk, but far more than expected if no winds had escaped. Galactic winds explain this enrichment. They also explain the heat of the halo. Supernovae in the disk pump energy into bubbles that rise and burst, stirring and heating the coronal gas above and below the plane. The aqua supershell offers an example. This immense structure stretches at least 550 light-years into the halo, driven by star formation and supernovae near the Aqua constellation from our vantage point. The Cygnus superbubble provides another example spanning 450 light-years and shaped by stellar activity in the Cygnus region. These are local cases. Structures like them likely exist throughout the Milky Way. Wherever star formation surges, the winds flow in two directions, upward and downward, forming a symmetry that stands perpendicular to the disk. The outflows travel where resistance is weakest along the vertical axis, where density falls most sharply. Some of this gas escapes into intergalactic space. Some returns descending onto the disk after millions of years in a galactic fountain cycle. Escaping gas steals angular momentum from the disk. Over billions of years, this loss alters the disk's rotation. Simulations reveal that galactic winds help regulate star formation by removing gas that might otherwise collapse to create new stars. Winds carry heavy elements into the vast regions between galaxies and scatter them across intergalactic space. They seed the darkness with the raw materials that future galaxies may one day gather. Here in our solar system, such winds feel remote. We drift far from the great stellar nurseries where these forces are born. Yet billions of years ago, when our sun was young, it may have emerged inside a region shaped by the same powerful winds. The early solar system might have been immersed in hot gas enriched with metals from nearby exploding stars. That gas became part of the solar nebula that formed the planets. The great chimneys rising above and below the galactic disk lift matter and energy into the halo. They act like arteries carrying the lifeblood of the galaxy into the emptier regions beyond. They link what we can see to the much larger structure we cannot. They also reveal that the space above and below the disk is not silent or empty. It is alive with motion and born from ancient violence. When scientists measured the temperature of the hot gas inside the local bubble with the ERO-SITA X-ray telescope, they saw something no one expected. The gas is cooler when observed toward the north galactic pole and warmer toward the south galactic pole. The pattern appears again and again. It is clear, it is persistent, and it is unexplained. No one yet understands why the local bubble holds this temperature gradient. The northern side is near 700,000 Kelvin. The southern side reaches close to 1 million Kelvin or slightly above. That difference is large, almost 50% hotter in one direction. For a structure about 1,000 light-year across, such an imbalance suggests unequal heating long ago. One idea is that the supernova or supernovae that carved out the bubble did not explode with perfect symmetry. If more stars died on the southern side, or if they exploded more recently, the gas there would have been heated more strongly. The gradient would then be a fossil imprint left behind by that uneven history. Another idea is that the interstellar medium around the region was not uniform when the bubble began to grow. The bubble may have pushed into gas with very different densities or compositions. If the southern gas was denser or richer in certain elements, it might have reacted differently to the shock waves. The final temperatures would then reflect those differences. A third possibility points to more recent events. Perhaps a later supernova erupted on the southern side within the last few million years. It would have injected fresh heat into that hemisphere without enough time for the temperature to even out. The gradient would fade slowly over the next 10 to 20 million years as the hot gas mixes. All these ideas show how limited our understanding remains, even for structures that surround us. We live inside the local bubble, yet we cannot explain its most basic temperature pattern. The challenge comes from our single viewpoint. We can only look outward from within. We cannot shift our position to see the bubble from another angle. Temperature measurements rely on the careful study of X-ray spectra. Hot gas emits X-rays with energies linked to its temperature. By studying the energy distribution, astronomers can estimate how hot the gas is. The ERO-SITA telescope scanned the whole sky in X-rays and built a complete temperature map of the bubble's interior. That map shows the north-south imbalance with striking clarity. The feature is real. It is not an illusion created by the instrument. Several independent analyses confirm it, but the cause remains unknown. We need better models of how superbubbles form and evolve. We also need more observations. Until then, the gradient stays a mystery. The imbalance may shape how the bubble grows. Hotter gas expands faster. If the southern side is hotter, it may extend more quickly than the northern side. This could distort the bubble and shift its center away from the place where the first supernovae detonated. Over long spans of time, the bubble might drift northward as the hotter southern gas pushes outward. For our solar system, the gradient brings no immediate danger. We sit inside the bubble, but the local interstellar cloud acts as a shield. It protects the heliosphere from the million Kelvin gas around us. Yet, the gradient still influences the wider environment we inhabit. If new supernovae explode inside the bubble, they will meet gas already shaped by this temperature difference. Their shock waves may strengthen the imbalance or erase it, depending on where they occur. The future of the bubble is shaped in part by its temperature profile, a profile we still do not fully grasp. The strange gradient we see reminds us that the cosmos holds more nuance than our tidy models suggest. Even vast structures reveal unexpected details when examined with care. The local bubble has been explored for many decades, yet only with the extraordinary sensitivity of the telescope did the asymmetry in temperature emerge. It makes us wonder what other secrets lie hidden in the data waiting for instruments of greater precision. Every second, hundreds of high-energy particles strike the atmosphere from above and from below. Despite their name, these cosmic rays are not rays. They are atomic nuclei, mainly protons, driven to almost the speed of light by violent events scattered across the galaxy. They fall upon Earth without pause, unseen and impossible to block. Their origins and their astonishing energies remain partly unexplained. Cosmic rays were first identified in the year 1912, when Victor Hess took instruments into the upper atmosphere by balloon. He found that ionizing radiation grew stronger with altitude, proving that the source was beyond Earth. The finding earned him a Nobel Prize, yet more than a century later, we still debate the origins of the most extreme cosmic rays and the processes that accelerate them. Most cosmic rays arise from the remains of supernova explosions. When a star dies in a blast, the outward moving shock wave accelerates particles to relativistic speeds. The shock behaves like a galactic scale accelerator, pushing particles back and forth until they reach immense energies. This process, called diffusive shock acceleration, can create cosmic rays with energies up to about 100 trillion electron volts. Yet some particles exceed even that. The most energetic cosmic ray ever recorded struck the atmosphere with an energy comparable to a baseball traveling at 60 miles per hour, all carried by a single nucleus. No known natural process explains such an extreme acceleration. Supernova remnants are not capable of this. Even the most powerful sources in the galaxy struggle to account for these extraordinary energies. Cosmic rays do not move in straight lines between their sources and Earth. Magnetic fields across the galaxy bend their paths, sending them on long wandering journeys. A cosmic ray may spend thousands of light years bouncing through magnetic structures before entering the solar system. By the time it arrives, its trajectory no longer points to the place it began. It carries no clear memory of its birthplace, and that makes the search for its origins difficult. Astronomers can track where cosmic rays appear to come from, but their directions are scrambled by magnetic fields. Only at the very highest energies, where deflection weakens, can a particle travel almost straight and offer a hint of its true source, yet such particles are extremely rare. Detectors must wait many years to catch even one. When a cosmic ray collides with molecules of nitrogen or oxygen in the atmosphere, it produces a shower of secondary particles. These showers cascade downward, growing in number until thousands or millions of particles reach the ground from a single cosmic ray. Detectors measure these cascades and infer the energy and nature of the original particle. The flux of cosmic rays changes with the activity of the sun. During solar maximum, strong solar winds and powerful magnetic fields deflect more cosmic rays, reducing the number that reach Earth. During solar minimum, the solar wind weakens and the cosmic ray flux rises. The atmosphere receives roughly 20% more cosmic rays in solar minimum than in solar maximum. Cosmic rays leave their mark. They ionize the upper atmosphere, creating electrical conductivity that shapes atmospheric chemistry. Some scientists propose that cosmic rays may influence cloud formation by producing ionization that encourages water vapor to condense. If correct, changes in cosmic ray flux could play a subtle role in climate across long time scales, though the effect would be small compared to other forces. Life on Earth is largely shielded from cosmic rays by the atmosphere, which absorbs most of the incoming radiation. Astronauts do not enjoy that protection. On the International Space Station, exposure to cosmic rays is roughly 150 times greater than on the surface. On a journey to Mars, the dose would be even higher. Cosmic rays stand among the most significant health risks for long-duration missions. They also leave their imprint on the technologies we rely upon. High-energy particles sweep through the delicate architecture of computer chips and can flip single bits, producing soft errors in memory or in logic circuits. Spacecraft and satellites encounter these glitches often. Cosmic rays also create false signals in scientific detectors, reducing the sensitivity of our instruments. Even voting machines have faltered, and people have pointed to cosmic rays as the cause. Above and below the solar system, cosmic rays fill the vastness of space. They come from every direction. They are accelerated by supernova explosions, by pulsars, by supermassive black holes, and perhaps by sources we have not yet uncovered. They carry clues about the most violent events in the galaxy. And they fall upon Earth in an unending rain. They are invisible travelers from the deep past of the cosmos, carrying energy from explosions that happened thousands of years ago in regions thousands of light years away. There is a frontier in space beyond which nothing can remain tied to the sun, not planets, not comets, not spacecraft. At that frontier, the pull of the Milky Way becomes stronger than the pull of the sun. Anything beyond that line belongs to the galaxy rather than to the solar system. This frontier is known as the tidal truncation radius, and it marks the true edge of the sun's gravitational authority. It lies somewhere between 100,000 and 200,000 astronomical units from the sun. The frontier exists because gravity weakens with distance. Near the sun, its gravity is overwhelming. It pulls on nearby worlds far more strongly than the galaxy does. But as you travel outward, the sun's grip fades quickly. The tidal forces of the galaxy remain almost steady because the galaxy is so immense compared with the solar system. At a certain distance, the forces balance. Beyond that, the galaxy dominates. At the tidal truncation radius, objects orbiting the sun feel equal pulls from the sun and from the galactic tide. Their orbits become fragile. Small disturbances that would cause only gentle shifts closer in can now eject objects completely. Across millions of years, the galaxy strips away anything that orbits near or beyond that frontier. This is why the Oort cloud has an outer limit. Comets cannot endure beyond the tidal truncation radius for billions of years. The galaxy removes them. The outer boundary of the Oort cloud, at about 200,000 astronomical units, aligns with calculations of the tidal truncation radius. This is not an accident. The galaxy defines the end of the solar system. The exact position of the frontier varies with direction. Toward the galactic center, tidal forces are slightly stronger, so the radius lies closer in. Away from the galactic center, tidal forces weaken, allowing the boundary to stretch farther out. The Oort cloud is not a perfect sphere. It is gently elongated along the line, pointing away from the galactic center, where the sun can hold on to objects at greater distances. Calculating the tidal truncation radius requires knowledge of the galaxy's mass distribution, including both visible matter and dark matter. Uncertainty in the nature of the dark matter halo leads to uncertainty in the frontier's position. Different models place it between 100,000 and 200,000 astronomical units, a factor of 2. That shows how incomplete our understanding of the galaxy still is. Beyond the tidal truncation radius lies interstellar space. This does not simply mean a region outside the heliosphere. It means a realm beyond the gravitational reach of the sun. Objects out there do not orbit the sun. They orbit the galactic center under the primary influence of galactic gravity. If the sun has objects beyond the truncation radius, they no longer belong to the solar system. They are interstellar wanderers passing near the sun for a short time. The idea applies to all stars. Every star has its own tidal truncation radius, beyond which the galaxy rules. Stars in crowded regions near the galactic center have smaller radii because nearby stars add extra tidal forces. Stars in the halo far from the center have larger radii because local tides are weaker. The sun's radius is typical for a star at our position in the galaxy. Some researchers have proposed that the sun may once have possessed a far larger Oort cloud, perhaps extending several times farther than it does now. Encounters with passing stars and slow erosion by galactic tides strip the outermost comets over billions of years. What remains is the inner core of the original cloud. It is the region close enough to the sun that after 4.5 billion years the sun still holds it. The tidal truncation radius marks the final frontier. Beyond it, you are no longer part of the sun's domain. You belong to the galaxy. Everything above and below the solar system, all the structures mentioned earlier, lies beyond this frontier or spans scales far beyond it. The local bubble extends 1,000 light years. The galactic halo stretches across hundreds of thousands of light years. Dark matter surrounds the entire galaxy. We are a tiny system set within structures of unimaginable size. The sun's gravitational influence reaches no farther than about 3 light years. Beyond that, the galaxy takes full control. What lies above and below the solar system is not empty. It is a galactic environment filled with hot gas, magnetic fields, dark matter, cosmic rays, stellar streams, and ancient features shaped across billions of years. We drift in that environment, sheltered by distance and by the sun's local influence. Yet the boundary remains. The galaxy encloses us, and at that final edge, the sun's power fades and the realm of the galaxy begins.